Welcome back, folks. We're going to talk about our first material property. There's a couple of them there's a handful, at least three, that we're going to talk about over the course of the semester. But we're going to start out with just one. We've been talking about pushing charge through some piece of wire. You can push charge through your body. You can push charge through the sky. All sorts of things. But when we can, we want to talk about the material properties that of the thing that we're trying to push charge through. Okay, so the simplest that we're going to talk about is resistance. So let me get down in the corner here, and different materials are going to have different values of resistance if everything else is the same. Some are going to be good conductors, certainly if you're thinking like copper, aluminum, gold, anything that you would create a wire out of. And some are going to be good insulators if you want to think about maybe glass or any number of rubber polymers or anything like that you might use as an insulator. But we can talk about their resistance based off of their physical properties all in the same way. Okay, so if we're going to talk about their physical properties, let's take a very simplified drawing. Again, it's my drawing, so it ain't going to be pretty. Hey, there's my three-dimensional wire. Can you tell it's a three-dimensional? It's okay. And then the inversion made it that lovely brown color. But here's our cross-section of a resistive element. Okay, so it's some round wire, and it's got some length, it's got some cross-sectional area, and then rho is its material properties. And we're going to relate those material properties in a really simple manner, and it's a nice, easy equation for us as far as equations go in engineering classes, right? So the resistance. Okay. Oh, I guess we should talk about units too. Let's talk about units. So resistance. We're going to measure it in ohms. Okay, so the unit is ohms. Okay, this is named after George Ohm. And I'm going to see how much you cheat. Okay. It's not going to count for anything. I usually like to ask in class, where do you think George Ohm was born? Because it's a pretty fun one. He's got a couple things named after him. He's got the unit of resistance. He's got one of our fundamental laws named after him. He's kind of one of the heavy hitters as far as circuit analysis goes. Where was he born? What country? So think about that one. Maybe I'll ask you to put it in the web work. We'll see. I haven't written those questions yet. But I love all of the wrong answers. So take a guess before you cheat and look it up. Okay, it won't count for anything if I put it in the web work. It'll be for fun. Okay, so the unit is ohms, and it gets a capital omega. Okay, so after our values, we'll see a capital omega, and we're going to read that as ohms. And the variable for resistance is going to be R. Okay, that one's nice and it makes sense. Very rarely are we going to have a time variant resistance, but it is possible to have one. So most of the time we're going to use capital R. I want you to be aware that you might get a time variant resistance, so we might see a lowercase r as well. Okay, so that's our resistance. Now, if we want to calculate the resistance of this resistive element, then we can do that. We can say the resistance is equal to the physical properties rho. We're going to multiply that by the length, and we're going to divide that by the cross-sectional area. Okay, and resistance is really telling us how much energy is required to measure a quantity of charge, or how to move a quantity of charge. How much energy is required to move a quantity of charge through this chunk of whatever it is. Okay, so if we make it longer, it's probably going to take more energy to move the same quantity of charge. Sometimes I think about this as cars on a road. If I want to drive from here to Waterbury. Who knows why? It's gonna take so much energy. If I want to drive from here to Scranton, Pennsylvania, it's going to take that much more energy. So as I make the material longer, and I want to move the thing further, then it's going to take more energy. So it's going to be more resistance. Okay, so as L goes up, as the length goes up, so does resistance. It's going to take more energy to move the same quantity of charge. Okay, if the cross-sectional area gets bigger, so if we're using this car analogy, which isn't a perfect analogy, but I think it works, we're adding more lanes to the highway, then it should be easier to move the same number of cars the same distance. So the resistance is going to go down. That doesn't work in the city of Hartford. Trust me, I've commuted through Hartford for far too long. But in resistance, it does. If I make the road wider, it's going to be easier for the vehicles to drive down. Less energy is required. Last one is physical properties. And as the physical properties change, if I'm really trying to abuse this car analogy, maybe I make the highway smoother, or I'm driving down a dirt road. It's going to take more energy to drive down the dirt road than it is a freshly paved highway. Okay, and that's really the physical properties that are encapsulated in this variable rho. Okay, so let's get some information on all of this. We've got lowercase l is the length of our material. That's going to be measured in meters. We've got the cross-sectional area. Okay. And that's going to be, we're still in SI units, so that's going to be measured in square meters. Generally don't have a wire that's a square meter in diameter, so it might be something smaller than that, but that's an SI prefix. Okay. And we know what to do with those. Okay, so, but base unit is square meters, and then rho is what we call the resistivity. Okay, and resistivity, we gotta end up with ohms. As we plug in all of our units here, I'm going to divide by, let's do this in a different color here. We know we have meters squared. It's going to be ohms. This is going to be meters. And then over here, I need whatever's necessary to make this equation work out. And in order to have that happen, this is the resistivity unit. This is going to be ohm meters. Okay, I'll put those in parens because they belong together. But this meter is going to cancel one of the ones in the bottom. That one's going to cancel the other one. And I'm left just with ohms. So the unit of resistivity is ohm meters. Okay, and that's a physical property that's going to vary with material type. So let's scroll down here, and I'm going to get a nice table of material types, just so we get an idea of the magnitude of some of these quantities. Okay, so here's a table of different material properties. So for right now, we're focusing on the first two columns. We have some lower resistivity materials up here at the top, and we have some higher resistivity materials down at the bottom. So it's going to be good conductors. Let me just write this over here. Okay, so these are good conductors. I was going to write bad conductors, but let's stay positive here. Good insulators. Okay. And then somewhere in the middle, and that middle is really going to be right around here. I'm going to focus maybe on these two. We call these semiconductors. They're not good. They're not bad. They're in the middle. But they're awfully useful for making digital circuits and transistors and things like that. Okay, so silver, copper, aluminum, tungsten you're going to find in light bulbs. It's going to be the filament of a light bulb. So their resistivity is really low, E -8. So clearly these are physics numbers, not engineering notation. Anytime you want to insulate something, so if you go outside and you look at your power lines, there's going to be glass insulators. I don't know if they're still making them out of glass. They might be ceramic, but we're going to be playing down here, and the resistivity is going to be much, much higher. We have 1 to 10,000 billion ohm meters for glass. Okay, that's considerably better than aluminum or copper or whatever you're making those wires out of. Okay, so you can get a big range of values in that way. Okay, this third column we're going to look at in another video. The resistance value changes with temperature. Okay, and different materials change in different ways. So this temperature coefficient is going to tell you how temperature affects the resistance of the material that you're analyzing. We don't do much of that in this class, but it's good to be aware of it. Okay, so all sorts of different resistivities, okay, for different materials. Now there's a related value and variable. It's very closely related, and you will run into it. So I think we need to talk about it. Okay, and that is conductance. Okay, it's just another means of characterizing the material's ability to move charge for a given amount of energy. And it's really pretty simple to relate it to resistance because it's just the inverse. Okay, so we use G, capital G, and it's just the inverse. Okay, so as resistance goes up, it takes more energy. As conductance goes up, it takes less energy. So they're really just inverses of each other. And I don't mean to insult your intelligence, but man, I can't figure out why some people can't get that. You can just solve it for the other one. Okay, so they're inverses of each other. The unit. Oh, this is one of the ones that has a legacy unit. Okay, so the SI unit was adopted very recently, and it's named after the German Siemens. Okay, so it's again named after somebody, so it's capital S. This is the SI unit. I'll write that in a moment. The old school unit that you may run into, that my old student ran into and was pretty happy about, is the mho. Seriously. Okay, it's ohm spelled backwards. Wait, it gets worse. The symbol for it. Okay, instead of an omega, it's an upside down omega. Okay, good luck finding that on your keyboard. So I'm really happy that we now have a proper SI unit for it. Okay, but you may run into the mho. It's just the resistance upside down or backwards or both. Who would have thought? Okay, so those are the ways that we're going to characterize how much energy it takes to move some quantity of charge through a material. Okay, we got to relate these. Oh, I'm excited. We're getting to our first fundamental law of circuit analysis. Okay, so go ahead. I'm going to ask you some web work questions quickly on this, but then keep going. You're getting there. We'll go on and we'll relate these with our first fundamental law of circuit analysis. There's 3, but this one's kind of the big one. Okay, so stay tuned and good luck.